I'll start 1.4 off with a review problem. So a little review of the trig limits. Remember, our first line of attack with any limit problem as I approach some constant is to simply plug that in. When I do that on this one, I get the tangent of 0, which is sine 0 over cosine 0 radians, which ends up being 0 on the top, over on the bottom I have x, which is just 0. So I get this indeterminate form of 0 over 0. So a line of attack with the trig functions that I told you was to make sure you get your trig functions in terms of all sines and all cosines. So what we're going to do is we're going to replace that tangent x with its equivalent, sine x over cosine x. And then that's all divided by x. Remember, that means that the division by x, if you want to even think of multiplying by the reciprocal or whatever, that x ends up being on the bottom of the fraction when you rewrite it. So it's not a complex fraction. That ends up just being on the bottom. And I want to maximize the use of those two known limits that we talked about yesterday, which is that the limit of sine x over x as x approaches 0 is always 1. So at this point, what I'm going to do is break that apart so I can maximize the use of that. I'm going to use proper notation here. So I'm going to say it's sine x over x times, technically, 1 over cosine x. Don't make that secant. Remember, we want the functions in terms of sine and cosine. So we would like to just keep that as 1 over cosine. So really, I still have sine x over x cosine x. I've just split it apart. Well, the limit of a product is the product of the limits. That's a property that we learned in 1-2. So really, when I break this apart using my proper notation, I end up with the limit as x approaches 0 of each of these separately. This we've proven to be 1, and this I can do with direct substitution. Cosine 0 radians, sorry about that, is the x value at 0, which is just 1. So my answer is 1. Note the process, though. Note the correct notation that I've used. Actually, even that should probably go in some parentheses. So make sure you rewrite the tangent. You maximize the use of sine x over x. Make sure you write the limit of a product as the product of the limits, and then evaluate. So that was just a little review. So now we're going to start talking about continuity, and this is a really important concept in here. So make sure you're not only just listening to these, but you're taking them into account. Notice I put a star here. That's anything that's on the test directly. So informally, we would say a function is continuous if you can trace its path without lifting your pencil, which makes sense. You can trace its path without lifting your pencil. Well, obviously that would mean it's continuous. It's got no breaks or gaps or holes or anything like that. But we can't simply use that as our formal definition of continuity. Graphically, we could use that. You know, if I have to pick up my pencil, I'm going to say it's not continuous. But we have to talk about what causes us to not have to lift our pencil. And informally, what causes us to not have to lift our pencil is that if there are no holes in the graph. Well, what does that mean in terms of the function itself? And notice I'm saying at c, which means c is some constant that we're approaching from both sides. So I would say that the function is continuous if there's no holes. Well, really what that means is when I take the function's value at c, it's defined. Or we could say f of c exists or is defined. All right? It means there's a solid filled-in dot there. That's not enough, though. Okay? Just to have it filled in, that's not enough. So let me graphically go show you what I mean by that's not enough. All right? So right here, if I were to come in like this and say, oh, I'm going to fill in that dot and have it be defined there at C, nothing's preventing this from happening. So on this graph, I'd say, well, f of c is defined. It's right here, maybe up at 2. But you can see I've got a gap in the graph. So now in my next part, again, this would be discontinuous. So I also have to add another part to the definition that I don't have any gaps at c. Well, how do I prevent the gap? All All right? So for me to prevent the gap, what I've got to make sure is that as I approach from the left, I end up at the same part when I approach to the right, which is basically a concept of limits. So I've also got to say that the limit, as I approach C from the left of my function, has to be exactly the same as the limit as I approach C from the right of my function. What that will do is prevent gaps. That's still not enough though, so let me show you a function that meets both of these criteria, but it's still not continuous. All right? So what I'm going to do here is I'm going to say at C, the function's defined. All right? Got a filled in dot, so I'm meeting criteria number 1. I'm also going to say that the limit as I approach C from the left is equal to the limit as I approach C from the right. Maybe that's down here at -2, and maybe I defined this at 2. So now I've got a function that is defined at C. It's got a nice solid dot. The limit from the left is the same as the limit from the right. They're both -2. But you'll notice that's not a continuous function. I have to lift my pencil. So I have to put a third criteria that says whatever this is defined at has to be equal to the limit. That hole has to be filled in right here. Only then, when I've met all 3 criteria, can I now draw this without lifting my pencil. Well, how do I write that in proper notation? Well, exactly what I said. I said I have to make sure that the limit as I approach C from both directions of the function, in this case right here, it'd be -2. I have to have that be equal to the value of the function there, which means I have to put this dot in that hole. And it's only when all 3 of these criteria are met that I have a function that's continuous. That needs to be understood very, very well. We're going to practice that more in the days to come. So when we do have discontinuities, we put them into 2 categories. This isn't as important as that definition, but we'll cover it. We have what we call removable discontinuities and non-removable discontinuities. Here's the book's definition. It says a discontinuity at C is called removable if I can make it continuous by just defining or redefining a single value. And then this is, well, what does that mean outside of that formal notation? Really what it means is, it is called removable if you can fill the hole. Fill the hole just by defining the value of f of c. And again, without a graph, that's a little ambiguous. And again, it's defining or redefining, but I don't want to write that in there. So what I'm going to do here is extend the page, and we're going to talk about some that are removable and some that aren't. All right? So let's put a little graph up here of a function that's not continuous, and we'll call it either removable or non-removable. So let's suppose I just simply had a real easy function that just had a hole in it here at C. And let's suppose that hole occurred at 4. That is a discontinuous function. If I asked you why, you'd say, well, of those 3 reasons on the previous page, you'd say f of c is not defined. There's a hole there. But we would call this a removable discontinuity, because what I can do here is just define by I could just fill in that hole. If I just said that I would like f of c to be defined as 4, then what would happen is that hole would be filled in and I could move along my merry way. So it's discontinuous, but we call it a removable discontinuity because I could just fill the hole by saying I want u to be equal to 4. Done. Here's another example of a removable discontinuity. So suppose I come in like this and like that, but at C, I actually am defined down here. F of C is -1. And let's suppose this is up at 1. We'll just make a fake function here. Obviously, this is not continuous. However, if I were just to redefine this, if I were just to say, you know what, I'm going to move this hole right up here and fill that in, it would become continuous. So it's basically, if you could just fill in the hole, we call it removable. So I'm going to say this is a removable discontinuity at C. How could I remove it? I could redefine. This one was never defined, so I would say I could define this as f of c equals 4. This one I could say I'm going to redefine f of c to equal 1. Basically, I'm going to move that dot up and fill in the hole in the ground there so I can move around. Well, what do they look like if they're non-removable discontinuities? There's basically two cases of this, and you can put yours below those other two. Here's one case. When it comes in like this and it's got this gap, this is discontinuous. If I were to say why, you would use the second reason on the previous page. Yes, it's defined at C to be up here maybe at 3. So f of c is defined, but the limit as I come in from the left is not the same as the limit when I come in from the right. Furthermore, I can't just fill in a hole here. By moving this up here, I have an infinite amount of problems down here. So I would say this is a non-removable discontinuity at C. And the reason it's non-removable is, again, I can't just redefine what happens here. Okay, so suppose I say, well, I want f of c. It already is 3. So doing that doesn't help me. You might say, okay, I want f of this one to be 3. I'm going to move that. You would have an infinite amount of them that you need to move up here in order to get this whole piece, let me grab it, up here. And that's not possible. You can only define or redefine the value at C. So we would say that's a non-removable discontinuity. And here's another non-removable discontinuity, is when you have an asymptote. There is no way that you can redefine what happens here. Yeah, suppose you say, well, I want it to be 1. Well, you still have a problem in that you're going to have to pick up your pencil someplace. So this one also would be called non-removable. Sometimes we call that an infinite discontinuity, where the previous one we call a jump discontinuity. So moving on to the next page, and I only have about 3 more minutes, so I'll go as fast as I can in the time given. It says, discuss the continuity of each. Well, the graph of 1 over x looks like this. So there is no way I can redefine this. I would say I have a non-removable discontinuity at x equals 0, or sometimes this is called an infinite discontinuity. The next one up, I've got a piecewise function. The first one, it's a line. At 0, I get 1, and then it's an uphill line. On this one, it's a parabola, but when I put in 0 here, I'm also at 1, so it ends up going like this. Because this hole was filled in, and because these both at 0 give me a 1 out, that's actually continuous on the entire number line. So you would say continuous everywhere, or again, it just says discuss the continuity. This one's not continuous, and it's a non-removable discontinuity. This one's continuous everywhere because that hole was filled in and these sealed up perfectly. I would say continuous on the entire number line. The next one, let's see if I can get this done in a minute and a half. Let's see what the graph of this looks like. We need to factor that g of x first, and we have a difference of squares on the top, and on the bottom, x minus 1. Notice these cancel out. So g of x is really x plus 1, provided x doesn't equal 1. At 1, I will have a hole in the graph. This one's important that you understand. It's the most important of the 3 of them. So let's go see what happens here. I would have the graph of x plus 1, but at 1, which would be at 1, 2, I would have a hole in the graph. That's the graph of it. So this is a discontinuous function, but we'd say it's a removable discontinuity at x equals 1. And if I were to say, well, how could I remove it? You would say, well, I can fill in the hole. I'm just going to say f of 1, you're actually equal to 2, and then I fill that hole in. So there you go. That's the end of the notes. Phew, I'm tired. We'll talk about these evens up here on the top of the page tomorrow.